I will talk about some paper I wrote recently in August, and I've been thinking more about the subject, and maybe there's a further paper coming along soon. And so, yeah, let me just begin some very general motivation, and then zoom in more into the problem. Okay, so whenever we compute some gravitational path integral, and we fix some boundary conditions, then of course we should integrate over everything. So we should integrate over the metric, but we should also sum over different topologies. So one example that has been explored recently a lot is JT gravity, where we have a two-dimensional bulk theory and a one-dimensional boundary theory. And for instance, we can compute this the partition function with a circle boundary. And now you can like sum over the geometries, so you get the disk partition function, but you get higher genus corrections where the disk has like this genus one hole, and of course you get all the higher genus corrections. And in JT gravity you can do that very explicitly. And one interesting thing that played some important roles is that if you now change the boundary conditions, so let's say we have two circles at a boundary condition, then we again instructed to fill in this geometry in all possible ways. So we get disconnected geometries that are just copies of the geometries we had here. We get also these kind of wormhole geometries. And by wormhole, I mean, so will talk only about Euclidean gravity. So when I say wormhole, I mean always like a space-time wormhole, not like an Einstein-Rosen bridge. Okay, and one more thing is that when we sum over geometries, I mean, like in first approximation, we might only take saddle geometries that satisfy the equation of motion. So for instance, in JT gravity, the disk one does satisfy the equation of motion, so it gives a dominant contribution. But a priori, there's no reason not to include other geometries that don't have, like topologies that don't satisfy the equation of motion. Okay. So, and here is just some general comments that including all possible geometries is really very important. And over the last 2 or 3 years, there was lots of progress in explaining various phenomena. And basically, lots of resolutions came from the fact that you should really include all the geometries, including these space-time wormholes. So some very breakthrough results here were that you could reproduce the page curve for the entropy of Hawking radiation, and basically like the second part of the curve is due to wormholes. And then also wormholes lead to this to the ramp, the linear region in the spectral form factor. And one thing that I will talk about more today is that the wormholes lead to this ensemble version of ADS-CFT. So basically, in the slide before, we computed this partition function with two circles, and we saw that it's not the same thing as if we would compute the partition function with one circle boundary and then square it. And the difference between the two expressions are exactly these space-time wormholes. And the common conclusion of this is that JT gravity is not dual to a single quantum mechanical system, but rather to an ensemble of quantum mechanical systems. Okay, so this is the general motivation, what we do in gravity, but really I want to ask a slightly different question today than I'm sure you have heard lots of talks on similar things, but I think I will talk about a bit of a different perspective on it. So, and mainly I want to ask, how does it work in string theory? And the first obvious remark is that string theory, at least in certain circumstances, should work very differently from the two slides that we saw before. And we know, of course, that there are ADS-CFT correspondences that don't involve ensemble average. So within string theory, the most famous ones are ADS5 times S5 and ADS3 times S3 times T4 or K3. And there's a duality that these are dual to Super-Mills or this symmetric product orbifold, or rather deformation of that. There's, of course, also the M-theory example, but that's even more mysterious, so I will not talk about those. Okay, so now the basic question is, how does string theory achieve a sum over geometries that somehow doesn't involve an ensemble average in the end? So the argument I showed you before seems super generic, that the partition function of some like disconnected boundary is not the product of the partition functions in semiclassical gravity. So usually we only consider string theory on some fixed background. So we fix our background and then we compute the string partition function on it. But really, at least to my knowledge, it's not really even clear. Let's say you have infinite computational power. What should you do to compute really the full string partition function given some boundary conditions? So let's say we fix some asymptotic ADS boundary conditions and we want to compute the string partition function on this background. I mean, like with these boundary conditions. So one very naive thing that you could do is to just compute the perturbative string partition function on every bulk geometry that comes to your mind and sum over all of those. So you could do some sum like this. So this exponential here, this is just the usual string perturbative string partition function. You get the sum of all the genera with some string coupling. You integrate over all the worldsheet fields. You have some worldsheet action. The end you need to exponentiate to also account for the disconnected worldsheets. Okay, there are several things wrong with this, some like more or less obvious things. So first of all, we only know how to include saddle geometries, even in principle, in string theory. Because the fact that we have a saddle geometry means that we have a consistent CFT. And so our string perturbation theory works. So when I say here, oops, summing over bulks, then a priori I can even only talk about saddle geometries. Another thing is that there will be in general some non-perturbative corrections that come from wrapping d-branes and so on. And these are also not clear whether they're captured. Maybe you can do some Borel resummation and get some non-perturbative features also out of that, but that's also not clear. So even in principle, to me at least, it's not clear what we should do to get really the full answer, let's say in ADS-CFT, to reproduce the full boundary.
Sorry, these d-brane wrappings, why wouldn't they be independent saddle points with open string boundary conditions?
Yeah, I guess you can, yeah. I will mostly only talk about like summing over geometries, like manifolds, but I mean, you're right that we could like understand them in, like put them in the sum here, yeah. And like say, okay, we understand as bulks also like bulks with d-brane boundary conditions.
Yeah, I have one quick just remark about this. You know, Ashok has recently been looking at this matrix model set up in great detail, and in his situation, he understands this thing very well, including what the role of you know, his idea is that you will go on these paths of steepest descent, and then in some situations he can sort of more or less prove that you have to sum over all saddle points, though sometimes with a factor of half.
Right, but also like in that there, for instance, like in the D, you need to only include some D instantons. So there are some ZZ instantons that are labeled by 2 integers, but for some reason you only have to, like one integer is always 1. And sometimes, as you say, there are like some factors of 1/2 that are mismatching.
Right, and he has some rough understanding about that, about
okay, maybe
what the steepest descent. I'm sorry to interrupt. But
I think, if I may just add, I think it's still an open question. It is in principle, I think, possible to figure out all these constants if we understand the manifold well, right? I think the main problem is we don't know how these various saddles are situated in the whole space of string fields. So it's not clear at this stage, but it's not impossible that everything will be understood.
Yeah, I agree. But yeah, so I agree that in secret one string theory we have it. I mean, you have it very well under control. But if you give me ADS 5 times S5, I would have, like, even in principle, no idea what I should do.
Sorry, Lorenz, you must go on, but let me just ask this. I mean, the lesson coming out of JT, for me at least, is that it's not just saddle points, as you emphasized. You know, it's configurations very far from saddle points. For example, for the double trumpet, which contribute in a very significant way. And I don't know whether coming out of D instantons and so on, there is some light being shed on that. Anyway, we can discuss later maybe. But
yeah, I mean, I will sort of like, I mean, a little spoiler is that this like question mark for me fails kind of spectacularly, this equation. So, yeah, But please ask me again. But I completely agree that that's also one of the main takeaways for me.
Okay. Thank you.
Thanks. Okay. Yeah, please do interrupt if there are further comments. Okay, so yeah, as I said, I want to look at this in string theory, and I will use one very controllable model, but one model that is sort of extreme. That's at the extreme opposite end of like our iteration than as in JT gravity. And so the model is string theory in ADS 3 times S3 times T4 that I already mentioned before, but I will further restrict myself to one unit of an SNS flux background. So I'm taking one specific background here. And we understood some years ago that with Rajesh and Matthias, that this theory is really, seems to be just dual to the symmetric product orbifold. The upgrade here from the previous statement is just that there's no deformation involved. But usually people say ADS 3 times S3 times T4 is due to a deformation of the symmetric product. So this is one very concrete ADS CFT correspondence where you can really compute many things. And so what I will do is to replace this ADS 3 factor in a second by some other 3 manifolds and consider the string theory on more general manifolds and try to sum over them. So, but let's first explain some aspects of this correspondence. So first of all, there's a number n here that appears here, which is the number of fundamental strings in the background. So you can think of this as some F1 NS5 brane system, and there's one NS5 brane and some number n of fundamental strings. And then the other very important comment is that this string is really tensionless. So I always call it the tensionless string, but it has nothing to do with like the flat space tensionless string that people studied long ago. And it's tensionless in the following sense. So string excitations are very light and there are massless as high as spin fields in the spectrum. So the dual CFT has really like some W symmetry. And so the generic string state looks kind of something like this. So if you look at the T=0 surface of ADS3, then the string winds asymptotically around the boundary of it. So most string states are really like so this is like the string at some particular time and it's like very large. So it's super like a flabby string. So it's really like the complete opposite of usual semiclassical gravity, where like most states are, all states are like point-like. And the very important comment here is that even the graviton is such a winding state. So there's no local graviton vertex operator. And so with this, you could immediately conclude that there's no local notion of space-time geometry. And let's better not talk at all about like some summing over geometries or something like this. But I would argue that we can still talk about background geometry in the following sense. So usually when we have some background geometry, then we can always define some worldsheet theory. So let's say we have some target space on, I don't know, K3 sigma model times something, and you get some worldsheet theory out of it. And now in this worldsheet theory, you can take the flux very small, and this worldsheet theory remains well-defined even at small flux. So,
sorry, could I ask? For K equals 2 and higher, is the graviton one of the short strings?
Yeah, it is.
Okay, so thank you.
This is only happening for K to 1.
Thank you.
Sorry, just since we are pausing, these are boundary gravitons, right? If I understand, there's no bulk.
Yeah.
Okay. Yeah. Okay. Thank you.
Yeah. Okay. And so when I talk about summing over geometries, what I really mean technically is summing over worldsheet theories, because that's the concept that I know that still makes sense, and I can talk about even in this tensionless limit. Okay. So now let's do this and consider the string theory on some different geometries. And the ones I will look at have this still simple factorized form. So I will take some hyperbolic 3 manifold, which is like locally Euclidean ADS3, but I will let this factor S3 times T4, I will not touch it. You could consider more general things, but I will stick with this. And this is still sort of tractable because every hyperbolic 3 manifold can be written as some quotient of the unique hyperbolic 3 space. So just if you take the universal covering space of that, it's always this H3, which is simply like a different name for Euclidean ADS3. So this has, in particular, SL2C isometry group. And so you can take some quotient or orbifold by some discrete subgroup of SL2C, and you can produce your favorite 3 manifold with that.
Lorenz?
So all we have to do is like you look at the theory that describes global ADS3, and you need to do, in the worldsheet theory, you need to do an orbifold to describe these other manifolds.
Lorenz?
Okay. Yeah, please.
Just a question. So when you say hyperbolic 3
Yes.
manifold, here the point of view is to just take the saddle points and to see what one gets.
Yes, I cannot say anything about the non-saddle points, so
Okay.
let's just start with the saddle points.
Yeah.
Yeah. Okay, so let's just do some examples to see how that works. So the example I will mostly stick to is that to take this group isomorphic to the integers. And so let's just say we take it to be generated by one group element, which we can take to be some diagonal group element. So let me call it maybe like that. So this is an SL2C matrix and generates a group that is isomorphic to the integers. And if you do that, how does it act on the boundary? The boundary of ADS3 is simply like a CP1, is the Riemann sphere. And on that just acts by some, let's say it has some coordinate x, and it just like acts by some multiplication, right? And so the fundamental domain of that group action is an annulus, and the inner circle and outer circle of the annulus are identified. And now, so that means that the boundary now becomes a torus of this orbifold space. And now you just fill in that torus, that gives you the bulk. And so maybe now it's not so hard to believe that you get thermal ADS3. And this tau I chose here is exactly the modular parameter of the boundary.
Sorry, Lorenz, just one more
Yes,
question.
please.
So in this case here, this ADS-CFT correspondence works for all n, right? Already. I just want to understand. Yeah, understand what is known about the system. I mean, that particular.
I will assume that it works for all n, but as I will like actually there's some problem that I will come to later. That string perturbation theory doesn't actually. I think it doesn't compute to like a fixed n result, but because like string perturbation theory doesn't keep the number of fundamental strings fixed. So what we will actually compute is not like some fixed n partition function, but like some grand canonical ensemble. But I will assume that this works for finite n, and like in particular, what I will compute gives evidence for that. It
Sorry, without summing over all the bulks, or I mean, after summing over all the bulks. I mean, just on ADS3, yes, what is the statement? The statement is just on ADS3. The statement is that of the perturbative agreement.
Yeah, so perturbatively, let's say like if let's say we start with global ADS and compute like some correlators in global ADS, then there would be no sum over like geometries because there's just one global ADS. And then the statement is that like this like matches even at finite n with the boundary. I mean, there are some problems with it, but I mean, I think the correspondence should work at finite n. The other question is how string perturbation theory is able to describe that, because finite n means finite G string. But yeah, so I will be able to compute this to all orders in string perturbation theory.
Okay.
And these partition functions.
Great, thank you.
Good. So yeah, so for this group, we just get like a donut, like a solid torus. And now, since we're doing Euclidean geometry, we can have a choice of our time, basically. So you choose your boundary time to be one direction. So you can either choose it to be this cycle, which is still non-contractible in the bulk, or you can choose it to be this cycle, which is like becomes contractible in the bulk. And this geometry is thermal ADS3, where you have this non-contractible thermal cycle, and in the Euclidean BTZ black hole, you have the contractible cycle. And of course, you can also take any linear combination of the two possibilities. and you get what's sometimes called this SL2Z family of Euclidean black holes. Within string theory, we can also look at conical defects. So there's no reason to restrict to smooth geometries because we're doing anyway orbifolds. And so we can in particular also take some group that is like Z times some finite order element Zm, and then we can have like some additional conical defect that runs inside this, in the middle of this torus. Okay. And just one other example that will also play some role.
Sorry.
Yes.
What about the geometry that is just Poincare patch ADS with two boundaries identified, two boundary circles identified? You know, this long trumpet kind of geometry that.
Yeah, I think you mean like the what's also called like cusp geometry sometimes.
Perhaps, yeah. This
is like the last geometry that I didn't mention that has a torus boundary. Actually, you can easily classify all the torus boundary geometries, and this is one that is missing. And you can understand it as like some m to infinity limit of the conical defects, if you want.
Yeah, and I was wondering, is that a legal solution in string? It sort of feels a bit singular, and
it's a legal solution, yeah.
And
I would like. I mean, it's still an orbifold, and this is a consistent orbifold. The orbifold group is Z times Z in this case.
And you don't get some sort of continuum that lives at the tip, which makes perturbation theory around this sort of singular.
I don't. There is a continuum, I think. I haven't looked in detail in it. So, like one way I always understand it is that it's the m to infinity limit of the conical defect. Because I mean, if you think about it, like the fundamental domain of the conical defect is like some slice of the annulus, and the slice becomes thinner and thinner, and at some point it's a rectangle, and it becomes the same geometry.
Okay, thank you.
Yeah, so this is like this sneaky way of getting the result for this cusp geometry, but I haven't tried to like honestly do the really Z times Z orbifold.
Thank you.
Yeah, thanks. Yeah, so as Shiraz was saying, so for the torus boundaries, there's like just a very small list. So this is like the complete list. So they're like the smooth geometries, then there's this conical defect, and then there's like this cusp geometry. That's it. So for torus boundary, it's actually kind of simple. If we want to compute something like torus partition function, then we will just need to sum over these. It's like very well controlled. Unfortunately,
could there be multiple defects?
Say again.
Could there be multiple defects going through this torus?
No, just one. That's I mean, essentially, you cannot fit more abelian factors in SL2C. That's the like. There's only one Cartan generator, so at some point you have to stop.
Okay.
Yeah, but there are no spaces, for instance, that have two torus boundaries. That's very annoying for me. So I would have very much liked to have like a space-time wormhole that connects two tori, because that would be very easy to compute. Unfortunately, if you want a space-time wormhole, then you need to do at least genus 2 boundaries. So you can do a space-time wormhole, which is now something like this. So there are two genus 2 surfaces as boundaries, and then there's some geometry that connects them. And the corresponding orbifold group is just the Fuchsian group that you use for uniformizing one of the Riemann surfaces. If you've never seen that, it doesn't matter for this talk.
Sorry, can I interrupt? I think you said there's no wormhole which interpolates between two genus 1 boundaries.
Yeah, I mean, like saddle geometry.
Oh, okay. It's not. It can't be saddle is the point. But I mean.
Yeah. There's obviously something like T2 times an interval, but it doesn't carry a hyperbolic metric.
So Lorenz, I would imagine the complement of the half link would have a hyperbolic metric on
it. Complement of the half link. What's the half link?
Half link is this one. Okay, so let me. Half link is this one, right?
Okay.
It's not the usual thing that you would have in mind, but it does have torus geometry.
But that's not torus boundary. That's like a cusp boundary, right? And
no. Complement of the link. So you drill out the link, drill out.
Yeah, but that also, I want the boundary to be at infinite distance. It should be the conformal boundary. It shouldn't be at finite distance.
Okay, so that I wouldn't know what the matrix actually looks like. But I'm saying I'm saying there seems to be a hyperbolic manifold with two torus boundaries.
I agree with this, but it's the torus boundaries are still at finite, like they're at finite distance from any other bulk point. And so it's not like a holographic setup.
Maybe. I don't quite know the metric, but yeah, I just wanted to.
Yeah, I think so. Like, yeah. But, okay, yeah, but I mean, one simple way of getting, or not simple, but one way of getting these space-time wormholes is by taking these Fuchsian group orbifolds.
Sorry, one Lorenz, question. If this cusp type geometry that you were talking about does really make sense, then perhaps you could imagine joining two cusps to each other at the singular point. It has, perhaps, it feels a little bit like this double trumpet kind of thing that people talk about.
Yeah, but the double trumpet doesn't have a cusp in the middle. I don't know whether I would count that as a.
But the double trumpet
maybe
was also,
we would count that as a wormhole.
Yeah, it was also not a solution to the equations of motion. So, and when you try to make it a solution, it becomes more singular.
I agree.
Okay. Yeah. Okay. Thank you.
Yeah. Okay. So now basically my main objective is to try to compute the thermal partition function in the boundary. So what we compute this thermal partition function, which for a reason I explain in a second, I denote by curly z. If this would be 3D gravity, what would we do? We would sum over like the thermal IAS, VTZ black hole, and all this SL2Z family of Euclidean black hole, include some one loop determinant on it. So in 3D gravity, it's actually one loop exact. So they're like perturbatively, that's exact. And now comes the story that we were already talking about. We don't know what to really include on top of it. So I think we should include non-saddle geometries. There's no reason to not include them. And then there's some discussion whether you should also include conical defect geometries or not. So yeah, basically this part was this classical Maloney-Witten computation, and now this is like in the last year. I find very exciting what is going on. Okay, so but now I want to do exactly the same thing for the string theory. So let's just take string theory, compute all of the perturbative string partition functions on all these guys. We can even compute them on those, but as I said, we cannot compute them on those. And let's see what we get. Okay, yeah, now comes the thing with the grand canonical ensemble. So as I said, this n is the number of fundamental strings in ADS3. And one thing is that string perturbation theory does not seem to fix n, just because if you compute some partition functions, you will take some exponentials and have like any number of string fundamental strings appearing in the string partition function. So this was already realized some number of years ago. And what you can do instead is to fix a chemical potential that is conjugate to n, and we let n vary. So from the boundary point of view, what we are doing is simply to consider the following combination of partition functions. So what we're computing is really this grand canonical partition function where we sum over all the n's and we weight them with some fugacity variable. Okay, so this is also the object that we will reproduce from string perturbation theory in some way, or we want to reproduce.
Sorry to keep interrupting, Lorenz. Just to get context. So suppose we were at k greater than 2 and we went away from this fundamental string ns5 point so that we turned on some other flux so that the long strings then become massive. Then presumably n is a good quantum number. Is that right?
So I think still not quite. So what's conventionally done is that you put like some very large number of background fundamental strings, and then you put some number of probe fundamental strings on top of it. And you usually say that the number of background strings is like larger than any other quantity in your system. And then n is like approximately a good quantity. But if you want to consider the system at finite n, which I want to do, there's like this split between background strings and probe strings is kind of artificial. I want to like just interpret all the strings as being perturbative strings.
Right. I was thinking the number of strings at infinity is a good number, and that's sort of what the field theory says. Oh, something like that. Or not?
Not
well,
really,
if you measure the flux
at
infinity.
I mean, the reason is because you have these winding strings. So these strings here, they're at infinity, and they're perturbative.
Right, but suppose you turn on one of these other fluxes. You're at k greater than 2, you turn on one of these. Then it can't go to infinity. So then the flux at infinity would just be fixed, right? It can't change.
And isn't it also related to the central charge, because it's 6k times k is the number of NS fibrils times n, right?
Right.
So, I mean, is it this n at infinity should be fixed, no?
Yeah, but if I mean, what I'm saying here is that I want to sum over all the n's. So these partition functions, they all have different central charge. I'm not keeping the central charge fixed.
Right. Yeah. So sure, you're free to sum over all the n's, but I was just wondering that in a theory, in a given theory, in the situation I said, it doesn't seem to me like n would fluctuate. Do you agree or not?
I'm not entirely sure, because like one counter argument to this is like what you're referring to is that the long strings go away, and that's of course true. But what doesn't go away is like winding strings. So there's still like some like this spectral flow sector.
But they're in the center. So now suppose I just measure the flux.
They're more in the center, I agree.
Suppose now I sit at infinity and I measure the flux of the strings. I count the number of strings by measuring their flux. That will not change, right?
Yeah. I agree with your argument. I'm still not entirely sure whether it's
okay. Thank you.
But I mean, I would be kind of puzzled that like if at this point it works in the grand canonical ensemble, and as soon as you deform slightly away from it, then it jumps to the canonical ensemble.
Well,
that seems a bit strange.
But it's connected with the fact that
perhaps that's the right thing.
But it's connected with the fact that these theories, if you don't turn on the extra flux, are singular. Right? The singularity is precisely the long strings going off to infinity. So if you desingularize them,
there's no long strings. So at k to 1, it seems not singular.
Okay, but there's some remnant of the singularity, because all your modes are the long strings. Sorry, I this is quibbling about words, but I'm just saying there's a difference between this and the other situations, a clear difference, that things don't go off to infinity. Yeah,
I agree.
Thank you.
Yeah, and Lorenz, just following up on the last two questions. When you say you sum over the central charge, the central charge is the thing that sets the ADS radius. So while it's hyperbolic space, you're kind of allowing, you're summing over things with different curvature. Is that?
I view it as like summing over different Newton constants, because like central charge is something like 3 L over 2. So yeah, but I usually tend to think that L is fixed and G varies. But yeah, I'm one of the two you need to vary.
But why is that natural? I mean, from a bulk point of view, or just yeah.
Sorry, the curvature of ADS is given by square root of the number of NS fibrils, right? There is no fundamental strings involved in it.
Say that again.
The curvature of the bulk ADS is given by alpha prime square root alpha prime times square root k, where k is the number of NS fibrils. There's no fundamental strings number of fundamental strings involved in the curvature, right?
Yeah, that's also right. Yeah, that's right. But in like the relation is like this. I think that's probably a more correct answer, because that's the 3 gravity perspective, and but I think that's a good point, that that the radius is still kept fixed.
Lorenz, one more question. Sorry, Lorenz. Yeah. Just when you say that that these geometries are kind of classified, the ones that have torus boundary with hyperbolic metric. I mean, one natural class of such spaces could also be hyperbolic knot complements. And is it the case that in all such cases the boundary is finite distance away? I mean, I don't know the metric, so that's why.
I mean, so there is like the statement is always that in hyperbolic knot complements, what you usually take as metric is that the knot itself is at infinite distance, but it's like a cusp boundary, right? It's just like the codimension is wrong. It's like a codimension 2 boundary, not
okay.
But now what you said, you can like, of course, drill out holes. And if you keep the same hyperbolic metric, then by definition, they will be at finite distance. I don't know whether you can choose a different metric such that they're again at infinite distance, but I wouldn't try to make a general statement now, but I thought that's not possible.
No, that probably may not be possible. Yeah, no, but what happens if the knot? I mean, this particular limit when this boundary shrinks, becomes very thin. In which case you would have infinite distance. So that why exactly is that a problematic limit?
That would be not like then the boundary would be like a codimension 2 boundary. I don't know what that means in ADS-CFT. Maybe someone knows, but that's like a 3-dimensional bulk with 1-dimensional boundary.
That's like a very thin torus or something.
Yeah.
So, okay. Fine, thank you.
Lorenz, I have a very remedial question. So when you sum over all ends, your G-string effectively G-string squared goes as 1 over n. So you are probing the strong coupling regime of string. So I mean, string perturbation theory doesn't work, right? So can you trust this full perturbative sum over genus expansion without considering the G-string effects?
Yeah, so that's a very good question. I'm very hesitant to trust it, but it works kind of perfectly. That's the most naive answer. So so it works to all order in G string, but it works. I hope I will show you what exactly works. But and there seems to be no back reaction or something that you have to account for, or like non-perturbative effects. But you're absolutely right to question it, and I don't exactly know why it works that well. It works very surprisingly well to me.
Okay, thanks. Yeah.
Okay, other questions? Okay, yeah, so the point of the slide is just that like from the boundary point of view, this is the quantity we're computing. And like the other thing that I just want to tell you, you don't have to memorize this, but like you can compute this very, very easily in the symmetric orbifold. In the symmetric orbifold, all you need to do to compute these partition functions. So it's like an SN gauge theory. And so you have to sum over all the SN bundles over T4. And that just means like you take N copies of T4, but going around like your cycles of the torus, I mean the T2, where the CFT is defined, you can permute these like copies of the torus in some way. So in other words, what you need to do is to sum over all the possible unramified coverings of the torus. And all the possible unramified coverings you can write by some exponential map, which generates the disconnected. So if here are all the connected coverings, and taking the exponential produces all the disconnected coverings also. And now you just have to sum over all the connected covering maps of the torus. And yeah, so this is like the sum over the degree of this covering map. And then within each degree, you can easily like see okay, I hope it's clear what like covering map means. But like if you have like a fundamental domain of the torus, you could like one covering map would like just add fundamental domain. So let's say this was our tau, and then like this defines a new torus with 2 tau. And so 2 tau is like a degree 2 covering of like the original torus tau. And yeah, now you just have to systematically sum over all of them, and you compute the original partition function with this new tau. So this is also sometimes called the Hecke operator. And this is like some spin structure, but it will not play an important role. Okay, so this is just a very rough structure that the symmetric orbifold partition function you can compute by summing over all the covering maps of your original base space. And if the base space was a torus, all the covering maps are also tori. The base space would be higher genus, like in the wormhole, then in the covering spaces you have like arbitrarily high genus appearing. So the torus is particularly simple. Okay. Good, but now let's come to the more interesting bulk computation. So as we said, we want to compute the string partition function on thermal ADS and all the other geometries that we discussed. and we can do it actually to all orders in G string. And that to all orders works because it's one loop exact. So it's quite simple. And one can actually show that it's one loop exact. So yeah, and we also said that the worldsheet theory is a Z orbifold, or because this group, this discrete subgroup of Z in this case, of the theory that describes global ADS3. And now the global ADS3 worldsheet theory was, so you can describe it conveniently in this hybrid formalism, where you basically describe ADS3 times S3 by some PSE 1,1/2 level 1 WZW model. Then there are some free fields for the torus, and there are some additional ghosts. And morally, this is quite a simple model. It's actually quite complicated, but morally it's very simple because this WZW model has a free field realization. So everything is free fields on the worldsheet. And so morally, because of that, the worldsheet theory becomes solvable, and you can compute many, many things. Okay.
Sorry, the one loop exactness because of supersymmetry, right?
No, not because of, okay, maybe it's because also of supersymmetry, but like technically supersymmetry almost never enters in the whole story. The one loop exactness, there's like some localization that I will discuss in a second, and the one loop exactness comes from this. I'm not sure whether you can view that as some consequence of supersymmetry or not.
Okay, so no, the reason I'm asking because you have BTC black hole in the bulk, so that's a there could be non-BPS solutions as well. That includes non-BPS solutions rather. So you are safe on that in that direction. That's what my question is.
Okay, I'm not sure I understood the question, but if I'm safe on that question, then
no, I mean you have BTC black hole that may not be BPS, right? In the bulk.
Yes. Yeah.
And so supersymmetry.
Oh yeah. All these, yeah.
Okay.
Yeah, all these manifolds are not BPS, like almost all of them. I agree. Yeah, I mean the spacetime wormhole and so on, they will break all the supersymmetries. Oh, and as you say.
Okay.
Yeah.
And
so
sorry,
yeah, but supersymmetry is in the background, but it actually doesn't play such an important role here.
So, and the one loop exactness is the statement that if your worldsheet is taken to be a homogeneous surface, you get 0.
Yes.
Okay, thank you.
Yeah. Yeah, you will see in a second why that is. And so if you believe for a second this one loop exactness, then we have to compute two things. So we have to compute the worldsheet sphere partition function. We have to compute the worldsheet torus partition function. So let's start with the torus partition function because it's a bit less confusing. And it's actually quite easy to compute. So you just take this PSE 1,1/2 WZW model plus free fields, and then you do this orbifold, and it's kind of straightforward actually. And the result is this. So let's just go through the pieces and see what they mean. So first of all, there's like a sum over 4 integers here. And these 4 integers are very easy to understand. They're just like worldsheet instanton sums. They correspond to all the possible ways, topologically distinct ways of embedding the worldsheet in spacetime. And like in spacetime, what I mean is like the far region of, so spacetime is like a solid torus, let's recall that, and the worldsheet is like this red torus inside that solid torus. And I want to embed that in like near the boundary. And so there's like it's like a map from a torus to a torus, and that's described by 4 integers topologically. Okay, and then let's go here. I already included for you this P. So this came from the grand canonical potential, and this paper of Kim and Parati that I mentioned. They explained also how to include this P in the worldsheet theory. So P is like a marginal deformation in the worldsheet theory that you can turn on, and it has a very simple effect on the partition function. So it just does that. Okay, and then like the most important thing in this partition function is this delta function here. So first of all, this partition function, of course, depends on the modular parameter on the worldsheet. That's this tau, but it also depends on the boundary modular parameter, because the boundary modular parameter entered in the orbifold, because the orbifold group depended on this boundary modular parameter. Okay, and the presence of this delta function says that this partition function is mostly 0, except if the two modular parameters satisfy some relation. Okay, and finally, maybe also something that we'll discuss this more in a second. So finally, one thing that here's a T4 partition function. If you look at it, it's kind of funny because it's a string. It's supposed to be a string theory, and so it's supposed to have like H transverse oscillator degrees of freedom. So you would have expected here to be something like T8 or something like that. So, but instead there's a T4. And so what happens in this tensionless string is that like many degrees of freedom cancel each other, just because essentially the space is too small to support any oscillations. So this like just follows from direct computation. That's like one of the reasons why this can even be due to like symmetric product of T4 and not something big. Okay, good. So let's look at this localization. And one other way of saying this, what we just said, is that the worldsheet partition function localizes in the modular space of Riemann surfaces, in this case genus 1. And on what does it localize? It localizes on all the holomorphic covering surfaces of the boundary torus. So the relation you can write like this. And whenever the two modular, yes.
Sorry, please forgive me. I'm not so familiar with this whole setup. So just in your previous slide, something that's confusing me is, I would have thought that the first quantized strings are able to propagate everywhere in the bulk of your solid torus. Why is their worldsheet being pegged to the boundary of the ADS3?
Yeah, thanks. Yeah, thanks. I should have explained that more. That's not at all obvious. So, so I mean, the reason is kind of it's not so easy to say. At least maybe Rajesh has a more easy way to say it. But ultimately, it just follows from like representation theory on the worldsheet. So if you look at like in usual ADS3 string theory, there are short strings and long strings, as you probably know, and they are associated to different representations of SL2R, which is like the principal series and the discrete series. And what happens in this, if you go to this tensionless limit, is that the discrete series that describes the short strings completely disappears from the spectrum, and only the like one particular representation of the continuous series survives. And so the interpretation of this is the worldsheet is very far out in the boundary. And yeah, there's actually a more direct way of also, if you look at semi-classical solutions, you can also see that like the radial coordinate of the worldsheet is always goes to infinity. And if you take the tension to be very small.
Thank you. Thank you so much.
Yeah. So I mean, this is also one of the main reasons why this even works. But it's kind of a disappointing reason. But you could say that there's not really bulk because the worldsheet never explores like the interior of the bulk fully.
I see. I see. Okay. Thank you. Thank you.
Yeah.
Lorenz?
I mean, this is, yeah, please.
Sorry, this argument rests on supersymmetry as well, right?
This one does rest on supersymmetry, yeah.
Yes,
I mean, this is
not
like
used in localization to genus 1.
Yeah, I mean, the localization, this one, yeah, I mean, maybe you can trace it back to the supersymmetry. Because
no, I mean, I'm just, going back to Somanshit's question as to what are, whether the supersymmetry is really necessary to argue for this localization on all the geometries.
No, this is, I mean, so like you can argue for it by just using this worldsheet theory plus the orbifold. And of course, I agree that there's like supersymmetry flying around in the background, but you really, if you look at the proof, you really don't need it. It's, I mean, you could also like chop off the S3 and like just only look at the SL2R.
But how is this argument not involve what you said about worldsheet sticking to the boundary and not exploring the bulk? Because if you lose supersymmetry now, then it will start moving all over the place, right?
I agree. Yeah, I mean, it's, if you want, it comes from supersymmetry because there's a supergroup, but then you make maybe supersymmetry manifest by using this free field realization. But what Rajesh and company recently, I mean, there's like a long list of papers that various people by now have written, where this like is proved in more and more generality. And basically, like first here we didn't use supersymmetry at all, so we got only like localization was consistent but not necessary. And then recently, Rajesh and other people have shown that it really, for this K1, the localization is really consequence. I mean, it's really there's no other way. It has to localize. And it follows from this free field realization. If you want, you can view the free field realization as some consequence of supersymmetry. Okay. That's fine for me.
Yeah, Abhijit, I just wanted to maybe clarify it. I think this localization is slightly different from the one loop exactness that Lorenz was talking about earlier. The one loop exactness, I think, is probably independent of supersymmetry, and you see it even in ordinary 3D gravity and so on. And so, so I think these are two slightly different. Was that your maybe the?
Yeah. There are two types of localizations. One loop exactness, and this other one. And then I was a bit I was mixing the two up probably. I mean, I thought the supersymmetry is requirement for both of them.
I mean, the one loop exactness immediately follows from the localization, just because now if you would have any, let's say the Burji would have genus, a higher genus, and then you would need some holomorphic map from some higher genus surface to a torus for it to be non-vanishing. I mean, that's on what it would localize, but such a map just doesn't exist. So I mean, the one loop exactness is an immediate consequence of this localization.
Okay, thank you.
Okay. So for the torus setup, it's very simple because it's just you need just a holomorphic map from the torus to the torus, and it's just very elementary to see that such a map exists whenever the modular parameters are related like this. And if they're related like this, you get a degree that is given by the determinant of this ABCD covering map. And you see that this degree exactly shows up here in the P. So the P measures how much a single string contributes the number of strings. In this case, it contributes the degree of the covering map many times. So even a single string, if it winds several times around the boundary, it can contribute to several string charges. Okay. And this property of localization, it's by now known in kind of a great generality, I think. So so basically, so here, as I said, it was proved in for global ADS correlation functions. So for correlation functions, this also works, and then you have ramified coverings. And so this is for the, but here it even works when the boundary is not a sphere, but it can be also torus. And here, this is the higher genus proof, and I'm trying to do now the arbitrary 3-manifold and arbitrary higher genus proof, basically. So basically, this property is very general, and you can just see it from some complex analysis thing. And as I said, because of this localization, the one loop exactness also immediately follows. But morally, the important thing is that this localization implies that we don't have to do any complicated integral over modular space of Riemann surfaces, but we can just sum over all the covering spaces. So it's just some finite or discrete sum. Okay, so with this prepared, we can now compute the string partition function. So what we want to do is to integrate over genus 1 modular space this worldsheet partition function that I showed you earlier. And it's really easy to compute. Before I show you the result, I should also comment that we should include the effect of the sphere in the genus 0 partition function. And this is sort of, first of all, the sphere doesn't follow the localization principle. That's one of the exceptions. So there is a sphere partition function that is non-zero. But unfortunately, I don't know how to compute it from string theory. If some of you know how or have an idea how to do actually this sphere partition function, that would be great. But the problem is that there's some the Mobius symmetry left, the Mobius group, and I don't know how to regularize it. But that's something I'm trying to do. It's really deep. So we don't know how to do it, but we can compute it just using gravity. So I will just for the purpose of this talk, I will just use the gravity answer and hope that it continues to be true in string theory, because the genus 0 is sort of the part that is captured by classical gravity. So I just take the classical gravity partition, sphere partition function, which in this language translates to pi times n times the imaginary part of the modular parameter of the boundary. And here n does appear, so the sphere partition function as computed by gravity would be in a canonical ensemble, but it's kind of straightforward to translate that back into the grand canonical ensemble. But yeah, so this would be great to do more vigorously. Okay. Good, but anyway, so once you do the full string partition function, you get a very simple result. So you get the exponential coming from the generating the disconnected worldsheets also, because until now we only looked at connected worldsheets. And then we had sum over ABCD. And out of the sum ABCD, if you do the integral over moduli space of Riemann surfaces, some of them disappear, and you get like just some sum over two infinite sums and like this finite sum. And in the end, you just need to evaluate the T4 partition function on different modular parameters. And now the surprise to me is that this agrees exactly with the symmetric orbifold partition function. And in fact, you can do it with any other background, and you always get the symmetric orbifold partition function. So the symmetric orbifold partition function you can either compute from thermal ADS on the BTZ black hole, any black hole, or even on the conical defect. Like you can always do the same computation, and you get always the same result. Okay. That's very surprising to me. So let's try to discuss what that means. So maybe the first comment.
Sorry, Lorenz.
Yeah, please.
Yeah, maybe you're going to say, but this is surprising because a priori you would have expected that the symmetric product should be equal to the product of all these things.
To the sum, yeah, but yes.
To the sum.
I mean, I'm summing over geometry.
Yeah. All right. Sorry, a sum of all these things, but that's not the case. I see. Okay, thank you.
Yeah, or I mean, at least not naively. You could like maybe think that you need to sum over all of them and then regularize or something like that. Mm-hmm. But I mean, it's kind of surprised. Like that's what also I like said before. It's very surprising to me that everything works that well. Like everything is like super canonical, and you just get on the nose the right answer without any need of like accounting for some very strange back reactions or something. Yeah.
So that means, Lorenz, that the exponent that you have here, that's modular invariant under the boundary modular transform.
Yeah.
Right?
Yeah, I mean, I'm surprising here that there's also spin structure. So this is only true up to also fixing the same boundary spin structure.
Okay.
I'm sorry, Lorenz, these various different saddles you had differed because of the different kinds of filling in.
Yes.
Now, you're saying your string doesn't explore that filling in. So basically, does that mean that all the saddles become identical effectively for the contribution to string perturbation?
I would say so, yes. But it's not like, at least string perturbation theory doesn't make it obvious, because you have to do the full computation and only afterwards you see that you get the same thing. For instance, also like the sphere partition function, obviously, so the result I showed you was like the sphere plus torus combined. You see the sphere on its own, of course, it's not modular invariant under tau to minus 1 over tau. So you need to combine everything, and only after you combine everything, you see that it's modular invariant.
I see.
So
yeah. So what is it true that the sphere plus any of these filling ins gives the same answer?
I mean, yeah, like the.
Sorry, maybe I'm misunderstanding.
So can you say again?
I'm probably misunderstanding. But did I understand right that you computed just one of the filling ins? You didn't have to sum over them all to get your answer.
Yes. So this is, for instance, like you compute on thermal ADS, you compute the sphere on thermal ADS, the torus on thermal ADS, you sum them up, you take the exponential, and you get this.
Thank you. Now I understand better. So but if you do this procedure for any of the filling ins, you get the same answer.
Yeah, that's the statement.
Yeah. Okay, and therefore, if you summed over the filling ins, you'd get infinity.
Yeah.
Okay, thank you.
The sphere contributions for the different geometries are different. Is that right?
That's right. Yeah.
Okay.
Yeah. So this is only true. I mean, maybe this is like the geometric picture seems to almost make it obvious, because the like string is not in the center of ADS, and so all of these should somehow the same result. but it actual computation makes it not obvious at all, because the sphere partition function is different for all of them, and like only if you combine everything and compute the full result, then it comes out to be the same.
Okay.
So maybe it's just a formalism problem. I don't know, but.
This answer that you have here, since I mean, for the modular, I mean, once you've computed it, the modular invariance under for the boundary modular parameter, that makes it manifest that it will be the same for the whole SL2Z family, but the conical is not related by any simple. But there, so is it that, I mean, is it that this answer has some addition beyond modular invariance? It has some additional symmetry, or how does it? I mean, the answers, the agreement, is it sort of because of some non-trivial identity, or does it come out to be exactly the same? I'm just trying to understand.
Right. So let's good question. So so if you would do the BTZ black hole, essentially what you would get is like there's also a sum over 4 integers, but the role is not here of like basically these 4 integers are permuted. Their role is different in the final.
Yeah.
So for instance, in the BTZ black hole, you would like exchange like some like basically some twisted sectors would be exchanged.
But the
conical defect.
Conical defect.
Yeah. So conical defect, if like there's an additional orbifold, and the untwisted sector of that orbifold looks also like that, but basically it's only like many things are like multiples of the additional conical defect angle. Like there's some like, let's say the defect angle is 2 pi times 1 minus m to the minus 1, and then like I think I don't remember which one, but a or d was like a multiple of m. Like you get only like the mth twisted sectors. But then you include also the twisted sectors of this Wiltshire orbifold, and that fills you in exactly the missing twisted sectors. Does that roughly answer the question?
I just wanted to understand how it kind of fits together. Thanks there.
Yeah, but I find it non-trivial and kind of surprising.
Sorry, I want to ask you something that you just explained to Siraj. So let's consider just the genus 1 partition function. So your worldsheet is sticking to the boundary. Your worldsheet is not exploring what lies inside, deep inside.
Yeah.
Then why shouldn't we expect just the torus 1, the genus 1 partition function to be equal for all the geometries?
Okay, yeah, naively we would.
Because asymptotically, sorry, carry on.
Yeah, so this is not quite the case, because only like that's probably what the question is getting at, because you're like only if you sum with the sphere you get something that's equal for the geometries, right? So it's not true that this torus partition function doesn't know anything about the geometry, even the bulk. But yeah, I don't know why. Like geometrically, I would have also expected this, but I guess like one way of saying it is that there's the conformal anomaly also in the boundary. So we know also like the result that I wrote down here does depend on the like how you choose your metric in the boundary. And I don't know. So so the sphere partition function depends on the conformal anomaly also somehow. So that's what makes the computation, I think, also hard. So also the torus needs to like cancel some parts of the sphere. I mean, it's like conceivable that also the torus depends somehow on this conformal anomaly. I don't know, probably this doesn't answer the question, but please ask more.
Okay.
So I have a very stupid confusion. I thought the sphere and the torus partition function are different orders in G string. So how can a discrepancy in one be cancelled with the other?
Great question. So the stupid way of seeing is that 1 over G string squared that appears in the sphere partition function is n, right? It's like because that's how the G string and n are connected, but you could also have you could make some energy n state by just taking n different genus 1 strings and like that have all energy 1, roughly speaking. So that's how they can compete. But they can really only compete because of this grand canonical ensemble. If we would compute in a canonical ensemble, then I think that's not possible.
So the low energy part of the spectrum just agrees on the nose of the torus. It's only the very highly excited stuff that require mixing with the sphere. Is this right?
Yeah, that's right.
Thank you.
One more stupid thing that I would ask you to show. If you have the solid torus where you have thermal ADS, how would you draw the sphere inside that sticks to the boundary? I mean,
the sphere doesn't stick to the boundary, I would say. The sphere, because like the torus, you can like do the representation theory and the worldsheet, blah blah blah. Like what I said to you before, that there are no discrete representations, but that's not possible on the sphere, right? Because there's no Hilbert space interpretation. So the sphere has no reason to stick to the boundary. I think the sphere explores everything.
Everything. Okay. Okay. So spheres knows about what's deep inside the bulk very well. I mean.
Yeah. And also the sphere doesn't follow this localization principle.
I see.
Like the proof breaks down if you look at the sphere.
Right.
Like sphere without any operator insertions. That should be clear.
Okay. Okay. Thanks. Yeah.
We're talking about correlation function. It does. Okay. Other questions? Okay. If not, let's go on, and maybe then there will be more things. So yeah. By the way, so I think I'm already over time. So. Please tell me if I should speed up or finish.
No, go ahead, Lorenz.
Okay. Yeah.
Take your time.
So yeah, so the obvious thing that we already said is that like it seems like instead of having something like this, that is kind of the equation that we had in the beginning, at least the naive version, that we should sum over all the possible bulks and compute the string partition function on it. We should just do that the string partition function is the the symmetric orbifold partition function we get by taking the string partition function on any bulk geometry and not like summing over them. And it seems also that if we would sum over geometries, we would overcount states. So in particular, that means that you can, if you take one state in one bulk geometry, then you should identify it with some state in another bulk geometry, right? That's the consequence of this. If we say that the partition functions are equal, then we should in particular find every state we should find in, like there's a realization of every state in any bulk geometry. So that's, okay. So let's see more explicitly that this indeed is the case. And yeah, so how would you do this? So we can, for instance, identify the ground state of the BTZ black hole with some very highly excited string state in thermal ADS. So if you take the BTZ black hole, which I put here, and take the ground state, so that just means you have like some not highly excited strings on it. In this tensionless limit, they're still actually winding, but they're not winding a lot. Then we should be able, if this is really true, we should be able to identify this with some very highly excited string state. And okay, so what's the state? So you can find it by just taking the answer of thermal ADS partition function that I showed you before and show by what is it dominated in some high energy limit. So we know there's like a, okay, I will discuss Hawking page transition in a second, but like in the BTZ black hole dominates the high temperature behavior of the partition function. And in this case, there's also like a worldsheet configuration that dominates the high energy behavior. And in this worldsheet configuration, the worldsheet winds many, many times around like the spatial infinity of thermal ADS. And like so this worldsheet is like highly winding. So it's like, has like a very high spectral flow and it's very excited. And so the worldsheet modular parameter, that's another way of saying it, is related to the boundary modular parameter by n. So it's like basically winding a non-perturbatively large number of times around the boundary of ADS. Okay, and yeah, so here again, I was asked before whether we should trust this analysis in this regime, and that's like the main questionable thing. I'm not sure whether I should trust, because you need like really like non-perturbatively large winding numbers. So because n is like 1 over g string squared. And so that's so there's essentially, you can interpret this as being that there has to be like some back reaction, because the string, even though it's a perturbative string, becomes extremely heavy because it winds that many times around it. And so you can like interpret it as changing the geometry, which indeed it seems to do. Okay. Yeah,
Lorenz,
just to give you one, yeah, please.
I mean, the fact that the partition functions agree and you know, from there you go on to identify states, right? So, but I mean, when a partition function of the CFT, let's say just the CFT is modular invariant, does one really expect that the states would agree in both the pictures? Just in the simple context of CFT. I mean, don't we have the Cardy formula where the density of states at high energies matches the contribution to the ground state, right? So there could be things of that kind.
I think, so are you objecting that like I'm saying that this state is this state? I mean, what I mean actually is like not really exact, the statement. I mean, like there's like first of all, there's like a collection of will sheets that contributed the same order. And I would also like, I mean, if you have like some small fluctuation on this, you can maybe still identify it with the beat. I mean, the equality is meant to be like this, like BTZ black hole plus excitations dominate the high energy limit of the like the Cardy formula. And here, like this Witchy configurations plus excitations on top of it dominate the high energy limit.
Okay.
So I'm not sure whether you can really identify this state with this state. That's I think what you're objecting to, right?
Okay. Yeah, thank you.
So have you moved to Lorentzian space in this slide, please?
No, no, I haven't. It's all Euclidean.
Okay, so when you say states, what you mean configurations?
Well, I can talk about states in the boundary CFT, even though it's Euclidean, right?
I was thinking the bulk is Euclidean, right, or Lorentzian?
Right, and yes.
So nothing's really moving in time in the bulk. The time is a circle.
Yeah, but I mean that there, like in the boundary, there's like a Hilbert space which lives here, and there's a Hilbert space that here lives, let's say, on the outer circle, and so you can compute the partition function, and it's like dominated by some, like even in a Euclidean CFT, and so this is like the Euclidean path integral in the CFT, and I'm thinking on like what dominates the high energy limit of that.
Actually, you're thinking of the world sheet states. These are not states in space-time. I find it confusing to think of states in space-time.
The same state.
Well, this time is a circle, right? There's no.
I agree. But I mean, maybe I'm used.
I don't understand. I mean, he's just talking like in any 2D CFT Euclidean. I mean, now forget about the world sheet. I mean, now you have a space-time partition function on a which can be interpreted as a torus boundary partition and the boundary torus partition function, and he's just talking about those. No, I mean,
right, but if you have a field Euclidean field theory, you have some configurations contributing to the field theory with Euclidean time on a circle, and the map between that and the actual states of the theory is not so clear. For instance, in a Yang-Mills theory, you have these holonomy configurations around the circle, which has no particular identification with states.
Right. Yeah.
Okay, let's think of this as like some string path integral, and then these are the configurations. Like.
Okay, thank you.
Yeah, string.
Thank you.
Yeah, maybe that's a better language. Okay.
So, sorry, just to say again, in string theory on where the space-time is taken to be a circle, there are often these winding strings around the thermal circle that play a big role in the partition function. But yeah, confusing to associate those with states.
Exactly one of those. Right.
Exactly, and that's confusing to associate with states because when time is infinite, nothing winds around time. Right? In Lorentzian.
Yeah, but you can identify this with states in the, there's a torus boundary. This is computing the torus partition function of the boundary, and the torus partition function of the boundary like computes the spectrum over
if by states you mean worldsheet states, I have no question. If you're saying that the states in spacetime, I don't understand. But maybe we are saying the same thing. Because the spacetime time is identical.
Is it clear what I mean by this equality? Like, yeah. So like, to give you one more example, like one more thing you can do is to try to identify the conical defect also from the point of view of thermal ADS. So that's just the same exercise. And now, like, you can do it, for instance, the identification, because like you can view the vacuum of this conical defect as the untwisted sector of the, like, there's an orbifold that reduces thermal ADS to conical defect, and you can view the vacuum of conical defect as the untwisted sector of that orbifold. So this is a physical interpretation. I cannot play the same argument as before with the high energy limit. And so what I would argue is that like the vacuum of this conical defect is the like the configurations where the string winds exactly m times around the spatial boundary now, but it can wind any number of times in the time cycle. Okay. So let's talk about the Hawking-Page transition. So usually, of course, we learn in gravity that we should like sum of all the geometries, and the thermal ADS dominates at low temperatures, and the BTZ black hole dominates at high temperatures, and there's a phase transition between them because this, yeah, this is the Hawking-Page transition. And here, the Hawking-Page phase transition really comes from different dominating worldsheet configurations, but in the same background. So for instance, in thermal ADS3, you can view this sum, you can view as a sum where you have like a string that winds many times along the thermal cycle. That's the analog of the thermal ADS. Like that's like a low, not highly excited state in thermal ADS. But the highly excited state in thermal ADS you get when you wind many times around the spatial cycle of thermal ADS. So this guy, if you look at it, dominates at low temperature and this at high temperature, and that leads to the phase transition. And again, here it's kind of confusing how the sphere and the torus mixes. So let me say it one more time, how this comes about. Basically, because there's a winding here, and this winding is like 1/g string squared many times. So it's like non-perturbatively large many times. And that's why the torus can be enhanced to also contribute as much as the sphere. Okay, but like also you could view that as like, if you wanted, you can view that also as the BTZ contribution. So you could rotate that picture and take the vacuum of BTZ. That's also fine. Or you could also rotate that. So this equivalence is really meant that you can do either this one or this one. Okay. So, but not both at the same time. Okay. Good. So this is kind of the story of identifying the states or the configurations. And so now I want to talk a little bit more about the boundary. So the boundary partition function and how we can recover semi-classical bulk from this story. But maybe before I go there, I ask for questions. Okay, so let's try to understand a bit more this grand canonical ensemble because it has kind of very interesting features, I think. So just to recall, that was our definition from the boundary point of view. And so the first comment I want to make is that at low temperatures, every partition function here behaves like q to the minus n half. It's just because the central charge is proportional to n, and that's just the usual q to the minus c over 24 factor. And so if you plug that in here, you get like a geometric sum, and it only converges when this condition is satisfied. So this definition of the partition function only makes sense if you take this fugacity variable p to be small enough. And so this is one instance I think you can interpret also as the Hagedorn transition. When you make there's no Hagedorn transition here as long as you make your p small enough. And how small you should make it depends on the temperature and the boundary. But what you can do, you have this primary definition that works if you make p small enough, but then you can analytically continue in p. And this is like a meromorphic function in p, and you can define it in the whole complex plane. And sometimes it's convenient to not use P, but like some e to the 2 pi sigma. Okay, and so what are the analytic properties? So in particular, it has very interesting poles. And basically, we already saw one pole, namely when we are going, let's go back here. When we're at low temperatures, then we can like view this, then we have this, this approximation. We can stick it in here and we do the geometric sum and we get something like 1 over 1 minus p q to minus 1/2. So there's a pole in P. And the pole, in, if you translate it to the sigma variable, it's proportional to the imaginary part of tau. And in some way, you can view this pole as being associated to thermal ADS. So this approximation that the partition function goes roughly like q to minus n/2 comes really from like the thermal ADS, like the usual gravity computation that we would do for thermal ADS. And in fact, it turns out that there's actually a pole for every semiclassical bulk geometry. So you have whenever sigma takes this form. So so it's then there's a pole in the partition function. And you can interpret these as coming from like the CD labels this SL2Z family of Euclidean black holes, and the M on top of it labels the conical defect angle. And for every such combination, you get like a pole. And yeah, this odd business and so on comes from some spin structures that are involved. But so the like first takeaway here is that there's no sum over geometries in this boundary partition functions, but still all the semiclassical geometries make some appearance. Okay, so there's like a very simple argument that you should expect a pole corresponding to any bulk geometry. So we can do it even more generally. We can go away from thermal ADS because at some point I also want to discuss the wormholes if I get there. So let's fix some manifold with the boundary being some surface. And now that the only comment is if you,
Lorenz.
Yeah, please.
Sorry, Lorenz. Just now I have a basic question, which I guess I should have asked earlier, but didn't realize. So in this, I mean, here in all these partitions where these grand canonical partition functions, all the partition functions that we computed.
Yes.
Yes. And should one not have expected this type of agreement that you expected for grand canonical partition function, that the partition function of the symmetric product orbifold should be equal to the sum over partition functions for canonical partition functions rather than the grand canonical one? But because now the grand canonical, I don't quite know what this means from physical point of view and why one should have expected anything about such a thing, because now we are summing over theories and so on. So this is kind of like this ensemble kind of thing again. It looks like. So could you say a few words about it?
Oh, okay. So yeah. So I mean, first of all, like if you do an ensemble average, you lose information because you're averaging over theories. Here you don't lose. This is like a transformation. You can go back and forth. Like you can extract a finite n result by doing some contour integral over this definition. That's the first thing, right? So you're not doing ensemble. I mean, I agree you're summing over theories, but you don't lose any information. So yeah, and then so the fact that you should still sum over geometries, even this grand canonical ensemble, is like every guy of those you would interpret as like sum over geometries, but that's like a linear definition. So you should still, I would still say you should sum over geometries even in this grand canonical partition functions.
I see.
From
so
the
you're saying for every instance you have the sum, and this is a linear operation, so the sum should translate to the grand canonical. Okay.
I would say so, yeah.
Sorry, go ahead, please.
Yeah,
you were saying something.
But yeah, so from the what's confusing from the gravity perspective that we were already getting at before, basically, is that the central charge usually in gravity is like something like 3L over 2G. Mm-hmm. So in this sum, you either have to like sum over bulks with different size or with different Newton constants. And that's kind of confusing from the gravity perspective.
But that's just because you wanted to compute the grand canonical one, right? Because you could compare coefficient by coefficient also. in which case you would not have to do this kind of a thing.
Yeah.
Right? That's just what you choose to compute. That's what this consequence of this is.
Yeah. And that's what string perturbation theory seems to compute.
Okay.
Sorry, but just to say about this, the reason we expect normally string theory to compute just one field theory is that infinity is rigid, right? And that infinity is where the field theory is. It seems to me that the key reason the string perturbation theory is computing the grand canonical partition function is that things are going to infinity in a very important way.
Yeah, but so one comment maybe that, for instance, in I mean, the grand canonical ensemble, for instance, comes also in ABGM theory. So also in ABGM theory, it might be that, like, okay, we don't have a good bulk description, but there, I mean, I view it because you have like a background that is created by M2 branes, and you're also scattering M2 branes, like probe M2 branes. So, and then, like, if you have a situation like that, it's also natural to look at the grand canonical ensemble.
Again, it seems to me the question is whether these probe M2 branes can go and hit infinity or not.
Yeah, that might be. Yeah, here, I mean, here the long strings don't have any analog in ADS5. So that's why in ADS5 ADS5 also from the string perturbation theory point of view, we keep the number of D3 branes fixed. We're not summing over that.
But in ADS5, we have giant gravitons that are big 3 spheres. The main difference is that they don't reach infinity. They're fixed size.
Yes.
Otherwise, I don't think it's qualitatively different.
Yeah, I mean, one like also what you said before with going away from the NSNS point. If you go, like, if you view this in the D1 D5 system, and then you could also, like, from my point of view, you like now you fix your number of D1 and D5 system, like D1 and D5 branes, and now you scatter fundamental strings, and then it's also very natural to get the canonical ensemble.
Exactly. It's the rigidity of infinity that is important.
Yeah.
In the sense of charges. And from that point of view, your theory is special in this moduli space of all theories. At least the k greater than 2 version of your theory is special, it seems to me.
Yeah.
Okay, thank you.
Yeah. Okay.
So the canonical, so the P, sorry, just the P enters just as a counting for number of strings, right? Essentially in the bulk. So canonical ensemble would have been a bunch of strings, basically a fixed number of strings, and then
but like asymptotic strings, that's important. I think that
I see. So that's why I see. Okay.
Because, for instance, the sphere partition function doesn't contribute at all to this P. So you can have as many spheres as you want, because they're not reaching infinity.
Okay, thank you.
Yeah. But I mean, you can introduce this P directly in the worldsheet. There's like a specific marginal operator that you can, like, it's basically the vertex operator that corresponds to the identity in spacetime. And that one, if you like, that's a marginal operator in the worldsheet, and you can turn it on, and the coefficient is this P.
Okay.
Okay. Good. Yeah. So okay. The argument for why there should be pole for every semi-classical bulk geometry is very simple. It's just like using usual gravity, but now in this weird grand canonical ensemble. So for every fixed n, you would have like S bulk, like the on-shell bulk action, which is proportional to n, because you could view like n being proportional to 1/g Newton. Or you could view it as being proportional to the bulk size, but it doesn't matter. In any case, it comes out as like the factor n. And then you get something that is bulk, that is n independent. Now, assuming that this thing dominates the partition function, you would conclude that like the grand canonical partition function has a pole in P that is looks like that. So that leads always to simple poles. But the kind of nice thing is that this seems to be even true, at least in the examples I've looked at, which is mainly this torus partition function. This seems to be even true for bulk manifolds that are non-dominating. So for instance, this, like, playing this argument, strictly speaking, would only work if this is the dominating one. But like for instance, the conical defect is never dominating, never dominates the sum over geometries. But it's still, you can find it as a pole in the boundary partition function. Okay. So one way of interpreting this is if you now tune the chemical potential, this sigma, to be close to one chemical potential where there's a pole, then so then the partition function is dominated by worldsheet contributions or covering up contributions. But really, maybe that I haven't made very clear. But I said in the beginning that the symmetric orbifold partition function is expressed as like a sum over all covering maps. And these covering maps appeared on the worldsheet because the worldsheet localized to all the covering maps of the boundary. So really, like these covering maps, you should interpret as the worldsheet. Okay, yeah, so here the symmetric orbifold partition function is dominated from contributions with a very large degree. So because like the pole comes from covering maps of very large degree, and if you go close to the pole, the divergence comes from very large degree covering maps. And so this is kind of the reason for me why, if you want some semi-classical bulk geometry to emerge, you should go very close to this sigma p. And so one way of interpreting this is that the semi-classical bulk geometry becomes a condensate of worldsheets. So I mean, these are mostly words, I agree. Like one concrete computation that you can do is that it's really a condensation in the sense of Einstein-Bose condensate. So if you look at like the number of copies that are, like for instance, for the thermal-IDS that are in the ground state, and if you go close to this bulk, to this pole in modular space, then you see that the fraction of copies in the symmetric orbifold that are in the ground state go to 1. So it's really like a condensate in the sense of Einstein-Bose condensate. But of course, this doesn't tell you physically how this works, this condensation. Okay, so I can basically summarize the this discussion of the analyticity by some phase diagram. So so here I've just plotted the imaginary part of the tau boundary, so that's 1 over temperature, and the imaginary part of the sigma. So recall that p was e to the 2 pi I sigma. So the larger imaginary part sigma gets, the smaller gets p. And basically here is the region where the grand canonical partition function, the definition converges. And so basically everything we said so far in both in the boundary and string theory, you should take in this region, because here everything converges and makes sense. But now if you lower this chemical potential, let's say, then at some point you hit some pole. And the pole can be either associated to thermal-IDS or to the BTZ black hole. So here I'm considering like the real part of this tau is 0, so it's like the non-rotating case. And yeah, so the Hawking-Page transition you see now here is like, it's basically associated to this intersection point, because here like BTZ black hole is dominant and their thermal-IDS is dominant. But like these poles, you can even see by analytic continuation below here. So you can analytically continue in this P, go down here, and you see even more poles appearing. And these red ones are the poles coming from the conical defects. Okay. Yeah, what I kind of find exciting, but I haven't looked too much into it yet, is that, so first of all, we saw that all the bulk geometries lead to simple poles in the grand canonical partition function. And so formally, at least, you can write that the grand canonical partition function you can get by summing over all the semi-classical bulk geometries and putting, like, you need to include the correct residue, and you write this pole here. Okay, and assuming that this converges, you know that this thing is like a meromorphic function P. So you reconstruct the full symmetric orbifold partition function. So, and so the Z infinity, if you look at it, is like the one-loop partition function in a fixed geometry at infinite n. So that's like one way of, like before I was telling you all the time that like, oh, there's no sum over geometries. But now, in fact, you can see also that you can view the symmetric orbifold partition function as a sum over geometries. But that's not how the worldsheet computes it. There are some problems because there are actually more poles, and I'm not sure whether I can, like, whether these more poles can be also associated to worldsheet like bulk geometries. So yeah, I'm not sure whether this literally works, this kind of fairy tale sum. But there's like one toy example where this wasn't kind of made more precise, namely if you take like this funny symmetric orbifold of the monster CFT, which is a holomorphic CFT. So everything is holomorphic and becomes much nicer. And so like you can express all these sums in terms of some J functions. And there you can really see that all this, like all the poles correspond to like some black holes, and you can do the sum over all the poles and recover the symmetric orbifold partition function. So it's kind of exciting that if you go to this grand canonical partition function, then you seem to get a very natural fairy tale sum. That yeah, always like in gravity and also in like, I mean, there's the classical fairy tale that works for the elliptic genus because it's protected, but to me it's not clear whether it's like a general thing that should work also for the partition function. Okay, so now I'm
sorry, Lorenz, just
yeah, please.
So you're saying there were additional poles other than that series that you wrote down, the one with 1 over m squared times tau boundary, and so there's a, so is there a simple way to characterize all the poles? Is there?
Yeah, there is. Yeah. So basically, the poles come. I mean, the poles come always from condensing worldsheets, but the worldsheets don't necessarily have to be in the ground state. They can be also in exciting state. So there's like, that's what I meant, like excited condensing worldsheets. So for instance, I guess you're for sure familiar with like, there's the product formula for the partition function. You can like write it as a product.
Yeah.
Over something like 1 minus, I might make a mistake. But there's some formula like this, I'm sure you have seen. And then you have to take it to the power that was like, when you wrote the original partition function as like sum over HH bar and with coefficient CHH bar. But like in this expression, you make most of the poles manifest. And you see that there's a pole, not only when you take this H to be the ground state, but also some excited state. So there's always a pole somewhere in P. Yeah. But these poles lie in the lower half plane, and not like these. If we're talking still about the torus partition function, then all these poles that I showed you before were in the upper half plane in sigma. So actually, this, like you see here, this I only drew the upper half plane of sigma. Right. Imagine part sigma bigger than 0, and there's an accumulation point of poles if you go to 0. But then on the other side here, down here, there are more poles. So these are these excited poles. And I don't actually know whether it makes sense to analytically, I mean, probably it does make sense to analytically continue also in the lower half plane, but it might be difficult because there's like a continuum of poles. It's like in a modular form where you have like poles on every rational number.
Yeah, but is it that these are the ones you showed are the only simple poles?
No. Okay, this M is supposed to be the twisted sector, but like M can still be 1 and H can be bigger than 1. Like H can be something else, and then this, I mean.
No, I meant.
Okay, you're saying because this C is bigger than 1?
Yeah.
Yeah, but imagine you have some winding state from the torus or something like this, and like this will only, and it's a ground state, so it has only degeneracy 1.
Mm-hmm. Yeah,
but I agree. There are higher order poles.
The simple ones are probably somehow special. Yeah, I would think.
Yeah, I mean, yeah, the simple ones are basically the ground states of things. So I basically discussed those that are associated to the ground state, to the vacuum of the original partition function.
So maybe that's what distinguishes them from these excited condensing worldsheets, that in some sense, probably the higher poles don't, in some real sense, contribute.
Yeah, but one thing that certainly, I mean, is there that is not listed here is poles that correspond to winding sectors in this T4. So the T4 has not only you can have winding and momentum on the T4, and they are still not degenerate, and they can appear sometimes here. And I'm not sure, maybe they're like associated to bulk geometries where like they're no longer of some form ideas 3 times S 3 times T4, but they could be like of some warp form or like some scalar, and the T4 takes some expectation value, I guess. But I'm not entirely sure.
Yeah. Thanks.
Yeah, thanks.
So Lorenz, one question. So this fairy tale that one usually talks about with the context of elliptic genus, there the thing on the left hand side is actually the elliptic genus in the canonical ensemble, right? Not the grand canonical one.
Yeah.
So qualitatively that is a bit different, or can be thought of in this way.
Yeah, I agree. Like maybe one exciting thing, or I think exciting of this formula is also that like knowing all the, like what we would usually compute are these quantities, like infinite n partition functions, right?
Right.
So very large n. And you can compute them on all the different bulk geometries. And now this formula tells you that if you know all these infinite n partition functions, you know the grand canonical partition function, and then you can do some contour integral and extract a finite n answer. So you can go from the infinite n answer to the finite n answer.
Right.
Okay. Good. Okay, so now I have like some comments on how like this condensing works a bit more manifestly, and basically what the problem here is that the symmetric orbifold is maybe too free to see how gravity should emerge. So like one way of saying this is that this covering surfaces or wood sheets, depending on how you interpret them, they're not interacting at all. So we're just talking essentially about a free field theory, and they're not interacting. But in gravity, of course, to get semiclassical gravity, we want some strongly interacting CFT. So we somehow want to turn on some interactions. And the usual classical way of doing that is to deform the theory away from the symmetric orbifold point. So there's a marginal operator in the twisted sector. You can add it to your theory and do conformal perturbation theory. And the lore is if you do that for a very long time, at some point you arrive at some point in modular space that is described by semiclassical gravity. And so yeah, this is incredibly complicated, and I have no idea how to do that. So I will like consider like some version of the toy model of that. And a very simple operation that you can do that sort of turns on some interaction of these covering maps is to disorder average the boundary CFT. And you can disorder average over the modular space of T4s, which is the Narayan modular space. So this is for me just some toy model to see how, like when you go to some more kind of strongly coupled point in modular space, how gravity should emerge more manifestly. So I agree, this is not turning on some interaction, strictly speaking. But
so always staying at the symmetric orbifold.
Say again.
You're averaging over the moduli of the T4, always at the symmetric orbifold point.
Yes, that's right.
Thank you.
Yeah, it's just, I mean, I would love to do it, like to do this deformation, but like this is my toy model of how you should get more manifestly semiclassical gravity.
So, and why do you say this is taking you towards semiclassical gravity?
Okay. Because we know already that the average partition function of T4 itself, you can interpret it itself holographically. So this was this recent work of these people. And so basically, whenever you, I mean, within semiclassical gravity, you want some ensemble average, right? Or you want like something of the sort. So yeah, doing an ensemble average, I think reproduces like is qualitatively more similar to semiclassical gravity than without. So
okay, thank you.
Yeah, so the idea here is to use this these formulas that if you now take the T4 partition function itself and you ensemble average it over this Narayan modular space, then you can write it as some sum like over cosets of PSL2C. So this is just again like this sum over the SL2Z family of Euclidean black holes. And you just take now the vacuum character on thermal ADS, and you sum over all its modular images. So in this case, I just took 4 copies. So this would be for both Sonic T4, but there's like a Fermionic version also. And this is like the one-loop determiner of Chern-Simons theory on thermal ADS. And yeah, this is not really Chern-Simons theory, because in Chern-Simons theory, there's nothing that tells us how that we should sum over some geometries. So instead, I will call it U1 gravity, this theory. So I don't know, like it's, I think still not settled whether this is actually a theory or not, but for at least some toy model that we can use. And so now I want to do the same thing for the symmetric orbifold. So I postulate basically that ensemble averaging this over like this Narayan moduli space gives some good model, or some more realistic model of semiclassical gravity. It will be not yeah, we will see.
So this is the Narayan moduli space of the T4.
Yes.
Okay.
Okay, so yeah, this thing you can compute by summing now over all bulk geometries, but not bulk geometries that fill in the original boundary, but they fill in the covering spaces.
Sorry to interrupt, but this is 16-dimensional moduli space over which you're doing an average.
That's right. Yeah.
Okay, thank you.
That's right. Yeah, so if you know how to compute this, you get for free how to compute that. And you can compute it by summing over all the bulk geometries, but the main difference is that you should not sum over bulk geometries that fill in the boundary, but that fill in the covering space of the boundary. So the boundary can be like some, say, torus, and the covering space can be like a disconnected sum of 2 tori, and now you should fill in that disconnected sum of 2 tori in all possible ways. So let me show you more explicitly what I mean. So here I have one example. So for instance, if the boundary is a torus and you have like a degree 2 covering of the torus, you still get a torus or disconnected sum of tori, and now you should fill in that. So your bulk geometry is something like filling in 2 tori. So you get like two donuts within like one in each other. So this is like the geometry is like thermal ADS times thermal ADS, and then you identify the boundary. So this is like the kind of bulk geometry that you have to sum over now. So you could also replace this by BTZ black hole, or this one by BTZ black hole. Like there are many, many more possibilities now than there were previously. You can also have this where the covering map is like not disconnected, but it's like a longer torus, and you fill this one in some way, this torus. Okay, so this is what I mean, like that you really should fill in the covering map and not the base map, like the base space. And so yeah, you can also say that like this expresses the symmetric orbifold partition function as like a sum of a multiply sheeted geometry. So this is like a 2-sheeted geometry that is identified at the boundary. And so these are like, you can like view as micro geometries. So they're like still basically the world sheets, but the world sheets filled in different ways. And so now they have like the world sheets suddenly have a bulk dimension. And in this picture is sort of easy to see what this condensation means. So the condensation, so if we go again with the chemical potential close to the pole, then these world sheets or these filled in world sheets condense to bulk geometries. And basically now you can get the pole whenever all these kind of these sheets of the geometry, they align. By align, I mean that they're all they look the same, like these two thermal ADS. You don't get a pole by taking thermal ADS times BTZ, like which would be like some interlocking geometry. But yeah, they have to all align, and if they all align, then they condense to like one semi-classical thermal ADS. That's kind of the idea. Is that clear what I mean? Yeah, so that's kind of my picture how this condensation works. But of course, this is still not a semi-classical gravity theory because all these sheets are still kind of independent. So so it's not true that we have some semi-classical bulk, but it's still like this tensionless string. I mean, there are slightly, like they do slightly interact because there are also bulk geometries that are like wormholes between the different boundaries. Okay, that's all I wanted to say on this. So if there are questions, please ask now. Good. So I'm almost done. The last thing I haven't talked about yet is the factorization problem. That was actually my motivation in the very beginning. So one question that you should still have is, how does this theory manage to not have an ensemble average? Like now I'm already, like I'm again considering the non-average theory, the usual symmetric product orbifold. So we can take this tensionless string and put it on this genus G wormhole, this Fuchsian wormhole that I told you in the beginning. And now you should ask, how is it consistent to have only single boundary theory and not this ensemble average? And the reason is essentially, again, the same that we said before. So that's why there's only one slide. So you can compute this, string partition function, the wormhole. By compute, I mean I cannot actually compute the full thing. The only thing I can do is to show that it localizes in moduli space of Riemann surfaces. But I cannot compute the actual value as we did before for the torus partition function. Because in particular here, now you need to include all the genera in the worldsheet theory. And the essential intuition is that, so this again localizes in moduli space of Riemann surfaces, no surprise there. And so what it means is that all the worldsheets kind of look like in this picture. So this black background is the space-time wormhole, and the worldsheets are also higher genus surfaces. I drew them in red. And they're all very far either to this boundary or to this boundary. So these are now we have two asymptotic boundaries of ADS. And basically there are no worldsheets in the middle because they cannot explore the bulk. And yeah, so the localization now tells you that the worldsheet either has to localize to covering map of the left boundary or right boundary. And using this, you can now argue, like even though I cannot compute this, but you can argue that the wormhole partition function needs to factorize. So there's basically one contribution that comes from worldsheets that localize to the left boundary and one that localizes to the right boundary. And like this wormhole partition function itself is like a perfect product. And in fact, I would expect it to be equal to some partition function that you compute on like some genus 2 handle body here times the genus 2 handle body here. So because again, I would expect it to be like completely independent of the bulk geometry and only depend on the boundary. And you should not even sum, like the lesson of not summing over geometries also continues to hold true here. So if you want to compute now the boundary partition function on like genus 2 surface times genus 2 surface, you are free to compute it on this bulk geometry, but you should not sum over geometry. So you can do it on this geometry and you get already a perfectly factorized answer. And so that's basically how this theory gets away in not having an ensemble average. Okay. Yeah, with this I would summarize. Okay, so yeah, let's summarize again the main takeaway messages that we had. So the first kind of technical result is that the worldsheet theory for this tensionless string theory on AES3 on any hyperbolic 3 manifold would localize in moduli space of Riemann surfaces to covering maps from the worldsheet to the boundary. So both are Riemann surfaces and you have these covering maps. Okay, and then one upgrade of this is that the partition function of the tensionless string, when you consider it on some 3 manifold times S3 times T4, that it only depends on the boundary of M3 and it doesn't depend on M3 itself. And so in particular, you don't need to sum over geometries. And in the context of this space-time wormhole, you don't need to include the space-time wormhole separately. And in particular, it leads to a resolution of this factorization problem in this instance, of course. Okay, and then one other thing that I stressed a lot is that the natural ensemble here is the grand canonical ensemble, and it's in particular the ensemble that string perturbation theory computes in. Then we also saw that the boundary partition function has poles, all these poles are associated to semi-classical bulk geometries, and close to these poles, the world sheets basically condense to these geometries. And so there's still a sum in which sense in which the boundary partition function is a sum over semi-classical geometries, but these geometries are sort of like simulated by the world sheets that condense into them. And these world sheets you could consider on any fixed background. And then one way in which this to me becomes more clear is if you disorder average the partition function of the symmetric orbifold over the moduli space of T4, and it expresses the symmetric orbifold partition function as a sum over these kind of multiply sheeted geometries or microgeometries or whatever you want to call them. And now that the condensation works, that all these different sheets of these microgeometries do align, and if they align, then basically semi-classical bulk geometry emerges. Okay, thanks very much. That's all I wanted to say. Sorry for taking it so long.
No, thank you very much, Lorenz, for a wonderful talk. Let's all unmute and thank Lorenz. So we have had quite a few questions already, but if there are more, please go ahead.
Hi, Lorenz. I had one quick question. Yeah, first I want to say that was a fantastic talk. Thank you so much for it. It was very clear and very interesting. Okay. Now, about the factorization issue, you know, the reason that naively there's a factorization problem is that you have two different boundaries that can be connected through a bulk. Now, it seems to me that sort of morally speaking, you are saying that in your theory, there's no bulk, and therefore there's no connection because the bulk becomes the boundary. So your resolution is very clear, but does it suggest a resolution for situations where we know that there is a bulk, something like ADS 5 times S5?
No, I mean, in fact, as I said, the resolution to me is kind of disappointing because it just says, okay, the bulk is the boundary. I mean, there's no bulk, so there's no problem. It's still non-trivial within string perturbation theory that it works. But okay, does it suggest in other circumstances? I think not. So in others, I mean, you might hope that some version of this story still holds true. In some, like, it certainly doesn't hold true in generality. But like, if I go back to the very beginning, maybe I shouldn't. But if I go back to the very beginning, I asked basically this question: how do we compute? So I had this equation. It's not yet there. So okay. So in what sense is this equation true? So, and you might still hope that in some sense you should not sum over the bulks, because all the bulks are like different bulks are already included by summing over all the genera and doing maybe a Borel resummation, and maybe that like around some fixed background, like some non-perturbative strings already include, I don't know, maybe part or more than part, I don't know, but of other geometries. And so in some sense, if you believe in something like this, then perhaps you could like compute the wormhole partition function on the nose, and it should give you like the full result, and it factorizes on its own. I mean, this, I don't know, maybe this is like very speculative. So, but I mean,
so is it
yeah, I mean,
is it related to the proposal that maybe the contour of the theory is such that these connecting geometries don't lie on it?
I haven't heard of this proposal. Who proposed that?
I don't know if anyone's proposing it. I'm proposing it. I mean, what I'm saying is that you've got some sort of you're going in field space to some place in infinity. Then you choose a saddle point. You know what is called steepest descent contour from infinity to infinity, and it goes through some saddle points and not through others. Those that it doesn't go through are sort of irrelevant. So maybe these exist as saddle points, but they just don't contribute to the path. And that's a natural suggestion. And I was wondering whether somehow what you're saying suggests that.
I mean, what I'm saying is, I think sort of opposite, right? Because I say that you should include the wormholes. I'm not saying that you shouldn't include them, but I'm just saying like including them is equivalent to not including them in some sense, because they just give the same contribution. But I mean, I feel it's sort of cheating not to include them, like just like ad hoc saying don't include the wormholes. That I mean, obviously this would give you a resolution, but
yeah, I agree. It would only be a resolution if you could understand the rules for path integrating well and show that the contour is. But I was wondering if you had really good understanding, sort of like Ashok is building. Maybe then you could do it there and just see. I'm sorry, this is unrelated.
Yeah, perhaps. Yeah, I fear I cannot say anything useful.
Thank you.
To extrapolate.
Hi, Lorenz. Thanks for the wonderful talk. I have 2 questions. So let me start with the first one. Could you comment on the normalizability of the states of the space-time theory at k = 1? For example, for k greater than 1, we know that the SL2C invariant space-time vacuum is normalizable, and the BTC black hole is also a normalizable state. So what happens at k = 1? Is there something funny happening at k = 1, or do we need to worry about the normalizability issues?
Right. First of all, you're probably aware that there's this paper by Givion Kutasov.
Yeah, but they didn't say anything about k = 1. They say what happens for k greater than 1 and what happens for k less than 1, but they didn't say anything about the k = 1.
I mean, here everything is. I would say everything is perfectly normalizable because you have a discrete space-time, like a compact space-time CFT, right, with discrete spectrum, and there's no continuum. So I think the question of normalizability becomes sort of easy. I'm not saying that I understand it from the worldsheet perspective, but from a space-time perspective, it's obvious that everything should be normalizable. Yeah, I don't know, I haven't tried to look from the worldsheet theory. I mean, you could look at this theory, this PSU 1,1/2 level 1, and see which states are normalizable and which are not.
Yeah, I mean, from the representation theory point of view, you mean?
Yeah.
Okay. And
I mean, what I expect is that everything should be normalizable.
Okay.
Delta function normalizable.
Delta function normalizable. Okay.
Well, what do you mean, Rajesh? Because delta function what?
No, I meant because this is sort of the continuous representation as p goes to 0, right? So they're kind of on the threshold of normalizability in some sense, because the j = half. So the j = half plus IP series. I mean, the kind of delta function normalizable, like momentum.
Yeah.
This is sort of like at some threshold. Yeah, it's a little tricky, perhaps. Yeah.
You mean that
but
the j =
there's
half?
no continuum in which sorry, Suman.
Exactly. So that's why it's a little delicate. I don't know in what exact sense, but some yeah.
Okay, and the second thing that I want to ask you, I think you explained it, but just maybe I missed some details. So in the thermal ADS, or when you have this non-BPS bulk, the worldsheet is sticking to the boundary because of the localization, not because of because of this moduli space localization. Is that right? That's what you said?
Yeah, that's part of it. I mean, actually, the localization doesn't show it to you yet. I mean, there's one more step that basically you once you're localized, you can the way that we argued for it with Rajesh was that now that you're localized, you can look for semiclassical solution that satisfies all the properties, and you see that the only such semiclassical geometry lives at infinity. So the radial coordinate is infinite. So that's there's one more step to argue for that.
Okay. Thanks. Yeah.
Sorry, one more vague question. In the first part of your talk, you sort of showed that all these different filling-ins gave you the same contribution. And so if you were naively to sum over all of them, you would get infinity. Now, the same situation arises if you are in a gauge theory and you fail to gauge fix completely. So you'd sum over all the gauge images and you would get infinity, but all infinity of the same thing. So I was wondering whether somehow there was a sense in which the bulk theory, there's some sense in which you should regard it as discretely gauged. And that would give you logic for keeping only one of these circles. It's a very, very, very vague question. But
yes, I think there's, I forgot now who wrote these papers, but there are these papers that say that they propose in 3D gravity something similar. Like they have like some large, diffeomorphism they want to gauge, and that's maybe somewhat similar. But I mean, of course, it's not like a gauge. Yeah, I think it's not like a gauge theory in the sense of gauge theory.
Well, this, if it works, it should be only happening at k equals 1. Because for k greater than 1, clearly these are different. Different fill-ins are different.
Yes.
Right, so.
Yes. Yeah, I mean, maybe this is also like one related thing is that so the boundary symmetry algebra is vastly bigger than Virasoro, right? It's like it contains like W algebra and like what Rajesh and Matthias called higher spin square, and so it's in some sense we're talking about the unbroken phase of string theory, where you have like you have this very big symmetry algebra. Like in the sense of Gross and Mende. And so you could wonder whether maybe this identification of bulk geometries is like some consequence of this, like this huge symmetry algebra. So that the answer is like completely already fixed by this symmetry in a given bulk geometry. And so that's why all the bulk geometries have to be the same. Maybe that's like one related speculation that I had.
Thank you.
But yeah.
So very naively, isn't it closer to what you would do in a string field theory, where if you were to sort of expand around one minimum of this thing, but if you could do it fully in some sense, you sort of automatically have the contribution of all other minima and so on. So isn't that the spirit of what you're saying, Lorenz, at least for this special case?
Okay, I agree completely that the thing that you should properly do and that I have no idea of doing, and probably Ashok would have knows much more about that, is like you should do the string field theory path integral. And with there you could like probably fix some boundary condition and you should just do the full integral. Right, and like string perturbation theory is in some sense like some approximation where we fix like some, like the metric part we fix, and then we do the string perturbation theory around that. Is that what you're?
Yeah,
asking?
It's more like somehow we have gotten lucky in this case and are able to do the sort of effectively what the string field theory would have done.
Yes.
And the yeah, and that's what the symmetric orbifold also captures. But yeah.
So, but you know, one thing that doesn't explain is that all these different saddle points are exactly the same, right? The fact that
that's probably an axis. Yeah, that has probably to do with some very special thing. I mean, the boundary theory has this modular invariance. It has some additional symmetries. Yeah, maybe the fact that it's exactly the same is even there, right? I mean, if I just expanded around one vacuum, if I could properly non-perturbatively compute a string field theory path integral, around any vacuum, I should be able to get the same answer, right?
But Shiraz, what you're saying is that there's like your question within string field theory becomes very precise, right? You're saying that in the field space of string field theory, there's like some discrete identification that you should gauge.
That's what I was wondering. I was wondering because you're really thinking of these different filling-ins as the same thing, right? Because there's no real bulk, right? So it feels like you're summing over the same thing many times. And that's what happens in a gauge theory. But I'm far from sure that.
But in what sense? Same thing. I mean, it's same mathematics, but as he said, one is like a condensate of very heavy strings in some sense. If you view it around the other background, the BTZ black hole or the conical effect is some condensate state, some highly excited state. but it's
but
not.
Both are string field configurations, and there's like some identification. I mean, probably this equality. I know almost nothing about string field theory, so forgive me if I'm saying something stupid. But like this equality, you could view as some identification of string fields, couldn't you?
Yeah, of the configurations.
It would be this gauge symmetry that would somehow explain there's no bulk. Like everything's living on the boundary. I mean, it's a very vague answer. Right. If you take
Shiraz, I'm trying to understand the distinction between between having the path integrals the same and the path integrals will be the same. That's sort of how the string field theory would be defined, right? So the additional identification is when you're identifying certain configurations. How do you frame it in the language of the string field theory? That is it that you're
maybe there are some chambers. Each chamber has one saddle point, and there's a discrete symmetry relating all of these chambers.
But what is that symmetry? I mean, the path integral sums over all the chambers in some sense. And therefore you get something manifestly the same, whether you expand about one chamber or the other chamber. But where do you see the identification?
But maybe if you summed over all of the chambers, you would just get infinity. Maybe the rules are that there's some additional gauge invariance.
Not summing over all the chambers, but summing over all the states. I mean, here he's including these configurations. He's including these configurations, right? And when you consider thermal ADS, you have the usual configurations, and then you have these highly excited winding configurations, which are, I mean, it's like supposing you do quantum mechanics with a potential V of x with multiple minima, and you have you'll have the contributions from the bottom, but of your perturbative minima, but you also have all these other excited states, and your path integral, when you sum over everything. So you've effectively included it, even though you're expanding around one background.
Well, I mean, it's okay. This is, of course, almost metaphysical, and I'm sorry for bringing it up. But for instance, if all you do is Borel resum the contribution around any given saddle point, you don't include everything. You include bits on part of your steepest descent contour, and then sometimes you need to add the Borel resum of other saddles on the steepest descent contour, as Ashok showed. I mean, the full Borel resum around the perturbative vacuum didn't include the contribution around the zero.
No. So you don't include it in an explicit way. I mean, you don't include it as a. I mean, there are two things you could do, right? It's supposing you could just do the exact integral.
If you do the exact integral, you're doing everything. But that's not exactly what's being done here, right?
I mean, you the exact integral, and you do everything, and therefore it includes everything.
But now suppose you do the best you can around any given saddle point, which is to Borel resum the perturbation theory around any given saddle point. That does not include everything.
But that's not what he's doing, right? I mean, isn't what he's doing more in the spirit of this exact integral?
Well, but in some sense, not really, because you're considering every bulk like saddle. And now you expand, like, I mean, since it's one loop exact, we can also say that we do the Borel resummation, right? It doesn't matter here. So yeah, you do the Borel resummation about every saddle point and sum of all of them. And
no, I mean, when you say that's just like almost like a variable. That's you're choosing phi equal to 0 as what your I mean, you have your integration, but you're effectively including all configurations in configuration space, even though you might be, choosing to write it in a form that when you do string field theory, you have to expand around some vacuum. I mean, you write the thing around some vacuum. You have you write a BRST operator, you write all the vertices, everything expanded around a particular vacuum. But in principle, that integral includes all the other vacua, the tachyon vacuum, the true vacuum, and so on. I mean, in the simplest examples we understand.
does one know abstractly how to like specify boundary conditions on string fields such that this space is asymptotically ADS3 or?
Yeah, no, and so no one knows any of that. So this is, like Shiraz said, metaphysical a bit, but I think trying to understand the spirit. To me, it seems like what you're doing is effectively you've gotten something like the exact string field theory path integral, and what you're computing is, and you can show that whether you compute it about this background or about that background, you get the same integral.
No, just to say, it seems to me is that he's taking the Borel resum about any given saddle point and claiming that is the full exact answer.
Why is the Borel resummation coming?
Because it's one loop exact. So it's no Borel resum. Yeah. I mean,
that happened. So as I said, I think in this case one is lucky because of this special properties, but that's an exact statement.
Around that saddle point. But
but it's an exact statement about. You can imagine some path integral where it's one loop. Like in localization or something, you do. It's a one loop exact statement, but it computes the whole path integral for you.
But not necessarily always. If it's one loop exact, it computes the whole thing, right? Like in.
In some of the localization
theory doesn't
do, right? In some of the Yang-Mills localization, you do. You get the whole path integral that way. That's what.
But sometimes you have to sum over many saddle points.
Sometimes. So, but if you are doing the full Yang-Mills path integral, and there's you have one Q exact minimum, and then you sum over. Then you do the integral around that minimum. You don't care whether there are other minima. In fact, normally when you do the localization, you add this funny thing, and the saddle point you're really expanding around is some strange, it's not even probably something very physical. I don't know. It's just, I'm trying to just take away the spirit of this thing. It's probably a matter of interpretation. And
I'll tell you what I was trying to do. I was trying to put in the sense that these were actually just all these saddle points were actually all the same, because the filling in means nothing. I was trying to see how the formalism would see that. So that was basically it.
I understand. There is, if you just take the mathematical statement of the equality of all partition functions, that to me can, if you just take that mathematical equality, I think that equality can be understood as just saying that integral of that partition function is the total integral, like doing some Yang-Mills integral on a sphere using localization. But perhaps there's more in that. And there may be a symmetry within that, especially because of this modular invariance.
By the way, I should point out that it's actually quite late for Lorenz now. It's 1 a.m. as I see on his computer. So
for me it's fine. As long as you guys want to go on, I'm completely fine.
Okay. Are you in California, Lorenz?
I'm in Princeton.
You're in Princeton.
Sorry. So the time here on your slides is a bit different. I guess that's.
The time I think is correct. It's one. One.
Okay. I got confused.
Yes. No, but my.
Okay, sorry. Yeah, I guess then we can continue the discussion.
My schedule is not kind of late these days. But maybe one also related comment, like one different way of seeing this, I think, is that as you said, there's some very big identification seemingly in the maybe string field theory space, field space, and I think it's also kind of similar than what Maxfield and Marolf was saying in this third quantization of gravity, where you have all these null states in the third quantized Hilbert space. So you have lots of unexpected null states there, And also here you have sort of unexpected null states that correspond to like geometries that look vastly different. And this is like a non-perturbative phenomena, that these geometries or these configurations become, that these are identified. So I think it's kind of a similar, like bit similar thing within string theory. Not sure, but.
Thank you.
Any more comments, questions? Okay, if not, let's thank Lorenz again for a very nice talk.
Thank you very much.